What is the best data to choose for your particular application or project?
The general rule of thumb is that the more clearly you can see the object in your imagery, then the more effectively you can detect it using Pictera. So, for example, if you have the choice between lower and higher resolution imagery, most likely you should go for the higher resolution imagery. Or if you're playing around with the imagery bands, then try to select bands that make the object you're trying to detect really stand out. It's important to note that this is more of a safe guideline to follow, but it's not necessarily a hard rule. In fact, some people have been able to detect things like camouflaged animals on the platform, or things that the human visual system would not normally be able to see. This is because the human visual system differs slightly in what it sees from what the machine learning's visual system is seeing. So, if in doubt, you can always use the free trial of the platform to test whether or not the machine learning algorithm that you're building is able to find what you're looking for.
If you're working with satellite imagery, there are a few factors to take into consideration. The first is spatial resolution. You can get some relatively high resolution imagery from some commercial data sources, such as Digital Globe. However, these images tend to be quite expensive. You can also get some free ones from things like Sentinel Hub. However, the resolution tends to be lower. This is not necessarily a bad thing. There's still some use cases and applications that you can do using Sentinel Hub imagery. However, if you're trying to detect smaller objects, this might be a problem. And the example that we show here, if you're trying to detect buildings, then you probably don't want to go any worse than 1 meter per pixel resolution. The other axis of resolution to take into account is temporal, as if you're going for some sort of monitoring use case, you want to make sure that your satellite of interest goes over a particular location frequently enough to make sense for your use case. Drone and aerial imagery has much higher resolution, which is nice, but they come with their own set of considerations. If the drone is unstable during flight, say because of wind, the clarity and sharpness of the images can be decreased. In addition, these images are not always at the same angle, as in they're not always pointed straight down, either due to the ground's angle or the drone's angle. These images typically go through a lot of post-processing in order to ortho-rectify them, which can result in distortions in your images as seen in the forest image here. Also, since the per-image ground coverage of lower aerial platforms is smaller, typically a lot of pictures are taken and then stitched together kind of like a panorama. However, this means that if an object is moving fast enough, it can appear multiple times in the same panorama. All of this can confuse either your or any processing algorithm's understanding of your image content. There are also some more practical considerations, such as the availability of the data in your region in the first place. If you don't have your own setup, you'll need to hire a drone or aerial service provider, which can become quite expensive quite quickly if you, for example, need frequent revisits of said region. Let's talk about the different types of data and imagery that you can use with the platform. There is often a lot of confusion with what you can process with Pictera, as the word that we use, imagery, is oftentimes confused with just being your standard red, green, and blue images taken from a camera. When we mean imagery, we just mean anything that can be represented as an image. An image simply consists of different bands, or in other words, channels of information. In traditional images, an image consists of a red channel, a green channel, and a blue channel. So each pixel of the image contains some red value, green value, and blue value. Your screen takes this and shines red, green, and blue light at the intensity represented by these values. Height maps from Lidar data, infrared data, and SAR, or synthetic aperture radar data, are just other forms of per pixel data, just like red, green, and blue. Thus, they can be processed just as easily. Even though none of these are actual RGB data, they can still be seen on your screen, which can only output red, green, and blue light, because your screen is just replacing these RGB values with these other data values. In the end, they're all just numbers. These other non-RGB types of data can also be visualized as grayscale if you take, say, SAR data, which only has one band of information, and just copy that data for each pixel into all three red, green, and blue channels. So your screen will just output the same amount of red, green, and blue for that pixel, resulting in a grayscale visualization. As far as what you can actually achieve with the data on the platform, as I said at the beginning of the module, if you can see it in the image, then you can detect it with Pictera. So now let's get to the examples. In this high-res RGB drone image, I can most certainly detect cars. I can probably detect the windshields on those cars, and I can probably also map the piles of trash. However, the resolution is not good enough for tiny objects like, say, ants, individual blades of grass, cigarette stubs, or the individual pieces of trash in those piles. This image is also RGB, but is coming from a Sentinel satellite, thus it's much lower resolution. I can still detect larger structures like warehouses or facilities, and I can also find the areas covered by, say, farm fields, water, or forest. However, because the resolution is 10 meters per pixel here, there's no way I can see things like cars, people, animals, or individual trees, as these will all be smaller than even just 1 pixel. SAR stands for Synthetic Aperture Radar. It's imagery taken from satellites, so it tends to be lower resolution. It can also have some strong artifacting or distortion, and the selection of different applications can be a bit narrower both due to these distortions as well as also just the appearance of the image itself. The nice things about it, though, is that it can see through clouds, and the images are not affected by differences in weather and daylight, which is certainly not the case with RGB imagery. So if I were to take an image of this scene at nighttime versus daytime, it would look exactly the same. From this image here, I can probably detect the ridges of the mountaintops, which is something that in RGB imagery would likely be much more difficult, since the ridges would blend more easily into the rest of the background, and also there could be, say, clouds blocking your view. This is an image that combines the red and green channels from an RGB image and the near-infrared data over the same region, simply by just replacing the blue channel with the infrared data. This is also called a false color image, and we'll show you how to do this for yourself in Module 8. It's good for things like trees and vegetation, and you can even get a rough idea of the vegetation health. The reason why I say you can get a rough idea, however, is that you might not have the desired sensitivity to get a super precise knowledge of, for example, how healthy your crops are, but you might also not need that level of precision anyways. Infrared data is also less affected by atmospheric effects, though there still can be a little bit of distortion. This is a height map image taken by Lidar, which is a laser sensor. Lidars can be fitted onto drones, so you can get quite high resolution imagery. However, there is no information at all about the color or texture of objects. It's just the height. So if you have an object that you're trying to detect that looks very different from its surroundings in terms of the color, but shares the same height as its surroundings, then in the LiDAR image it will be completely invisible. RGB images, of course, have no information whatsoever about height. So again, it really depends on what you're looking for in your images. If the distinguishing characteristic of the object is actually the height, then of course this is a good choice. LiDAR sensors don't go through clouds, though if it's on a drone, you'll probably be below the clouds anyways. And as I said before, LiDAR sensors are just lasers, which is a form of light. So if light can go through something, then so can LiDAR, and the appearance in the resulting image won't be affected. Like SAR, it's also independent of daylight. In this particular image, the things that I can detect here using LiDAR are probably trees or buildings. As a side note, SAR, infrared, and height maps are single-channel images, and you can even do things like combine them all together into a single 3-channel image, kind of like what we did for the previous false color image. You might ask if it always has to be 3 channels, as if you're already involved in the geospatial domain, you'll know that some geospatial imagery comes with a lot more. From a machine learning perspective, it's certainly okay to use and process all these channels at once, even if your screen can't visualize it. Currently on the platform, however, you're limited to just the first 3 channels of the image, though this is more just due to a technical limitation that we may choose to lift at some point. There are also ways to combine multiple channels of information into a single channel, though we won't get into that here. There is a lot to take into account when choosing the right data, and so there aren't any hard rules. It's more of a skill that you'll get used to over time. But here's at least a short list of questions to ask yourself when you are trying to make that decision, including things like, what spatial resolution do I need? What are the distinguishing characteristics of the thing you're trying to map or detect? Where is your area of interest? What is your desired temporal frequency? And perhaps most importantly, what kind of accuracy are you looking for in your solution? No solution is going to give you 100% accuracy, not even manual human annotation. The better suited your imagery is for the task, the better your results will be. But if it's too difficult to acquire that imagery, either say due to pricing or imagery supplier constraints, then you have to ask yourself, is it okay for me to go with imagery that could be less optimal, say at a slightly lower resolution, and sacrifice some accuracy as a result? That's up to you to decide. As you can see, geospatial imagery is arguably the most complex domain of imagery, not only because of the varied data types, resolutions, and ways to access it, but also simply because your images can be enormous. Think 100,000 by 100,000 pixel images with multi-gigabyte file sizes. Handling such large images comes with its own set of software engineering challenges to make the platform work at such a large scale, and not only in processing the image, but also even just in uploading and displaying it. We've built the platform to work on this type of complex data, and as a result, it also works on much more simple imagery. You really can get quite creative. Whether it's counting birds, red blood cells, stars, books, or even jelly beans, these are all things that you can try to detect with the platform.